We're very excited about the results or about today's inauguration, and we're frankly just really excited that the U.S. is officially going to be back into the Paris Climate Agreement. So for the three speakers here, this is the culmination of a really great day for us. So we're super excited to be here to talk to you about this initiative. So as Lorena said, I'm a practicing structural engineer at LeMessurier in Boston. And I'm working with Dirk and Lauren on the SC 2050 commitment program, which my colleagues will get into in a bit. I'm going to sort of set the stage and talk about the importance of embodied carbon, sort of introduce embodied carbon on the structural material side of things. And really my hope is that by the end of the presentation, you see the sort of emphasis or the rationale why the role of the structural engineer is so important for this effort. Of getting to net zero. I'll just start. 4 years ago, I was working on this very large project in Boston, and I didn't know what embodied carbon was. I had no idea. The term didn't mean anything to me, and so. But it happened to be at a time in my life where I was sort of trying to be a better steward of our environment, and so it sort of hit me one day when I looked out at the site. I said, well, what are we doing here, right? This can't be a zero impact to the environment. And so I started to do some Google searching, and I kind of found my way to the Structural Engineering Institute's Sustainability Committee, and actually found a sustainability guide that Dirk Kestner edited a number of years ago. And so I found a way to come up with the environmental impact by just taking these basic material quantities, which are much higher than any project I've ever worked on. So it was also exciting just to see how big this number would be. And so I just took some back of the envelope numbers and came up with a value of over 28 million kilograms of CO2 equivalent. And even at that time where I didn't really know how much that was, 28 million is a big number. And so I started looking into, where do all these impacts come from? Okay, and for me personally, I have to visualize these things. And so here are just some pictures of what I have listed for the different embodied carbon impacts. And I will tell you, a lot of this stuff is out of sight, out of mind, but on a personal level, a couple of years ago, as I was traveling in Malaysia, where they had a very large cement production plant. And that's not my picture with the 4 smokestacks, but that's exactly what I saw times 5, and it was quite striking and really hit home for me. And I know all of this hits home for all of you, and so it was that was a turning point for me personally, and I think probably for most of you had some similar experience to that. I am not a life cycle assessment expert by any stretch, but I think it's important for structural engineers to understand the basics of it. Excuse me, and that's about the most I can understand is the basics. So here, with any building, there is a life cycle, and there's different stages associated with that. And when I was looking into the embodied carbon impacts, they really show up in a lot of the different stages, whether it's material extraction, manufacturing, construction, and to a certain extent, the use case. If you're going through major renovations, there are certainly embodied carbon impacts associated with the materials of a renovation. But the more I looked, I sort of realized that the manufacturing of the structural materials is by far the biggest impact. And that's something that I'd like to just touch upon a little bit today. So here's a very approximate diagram of structural steel manufacturing and how you get to the environmental impacts. This was part of my personal learning curve. And so it turns out the structural steel manufacturing process requires a tremendous amount of energy and a tremendous amount of raw materials pulled from nature. Even in the case where steel is highly recyclable, you still have to break down that recycled material using a lot of energy and a lot of heat. And then on the flip side of the equation, there's a lot of emissions put back along with the water byproduct, dirty water byproduct. And so this is sort of emblematic of extractions from nature and emissions to nature. And so all of this stuff goes into, there are different LCI databases that track the impacts of all of the different processes, and then those sort of culminate into, and I'm skipping over a number of different things, but that all culminates into an actual environmental impact, like in global warming or ozone depletion or acidification, so on and so forth. There's many different environmental impacts, but when we talk about embodied carbon, it's synonymous with global warming. This is an example of that, where you take emissions from 3 different greenhouse gas emissions and you multiply them by what's called a characterization factor. And again, I'm skipping over a bit of stuff, but basically the point is that it's all being normalized into a single impact number, and that all happens sort of behind the scenes. And that was important for me, and I think it's important for structural engineers and basically people in general who want to understand embodied carbon, where these numbers come from, because even in my short time working on this stuff, even in my office, I have sort of dove back into some of these numbers, and so doing a little bit of research ahead of time has paid dividends for me personally. When it comes to structural materials, most structural materials have 2 sources of impact. One is they generally require a tremendous amount of heat, which is usually sourced from a fossil fuel source, which has a CO2 byproduct, and then there is some sort of chemical reaction that happens where there's an offing of CO2, so sort of a double whammy. That is very emblematic in the production of concrete. So concrete is made up of different constituent materials: cement, aggregate, sand admixtures, water, and then there's transport and operations associated with all of that. But really, it comes down to 85 to 90% of the global warming potential impacts are from the cement production. And so when you dive into the cement production, like I said, there's basically, you're basically breaking down limestone rock with a tremendous amount of heat, and there's a byproduct of CO2. And so as it turns out, 1 ton of cement produced releases 1/2 ton of CO2. That's not a particularly efficient system, right? So to produce 1 ton of cement, half of the byproduct is CO2, which for me, every time I see these numbers, it's striking. And then generally, depending on the numbers that you read, cement production accounts for about 7 to 10% of the world's CO2 emissions. Okay, that's a number that often grabs people's attention. If you are a structural engineer and you're struggling to convince people why the structural materials and the structural engineering world need to be involved with this, if you tell them that the cement production of concrete is 7 to 10% of the world's CO2 emissions, they're going to start listening. One thing that's really, really important to talk about here is a declared unit, functional versus functional unit, and specifically functional equivalence. It's very dangerous to just compare 1 ton or 1 kilogram of steel to 1 kilogram of concrete or timber without tying in some sort of performance metric to that. I'm a structural engineer, so I couldn't resist putting a shear and bending moment diagram in my presentation. And so here's a basic example of comparing a steel beam to a concrete beam, with the performance metric being carrying 50,000 pounds of load. And so here, in this case, the steel beam is 694 kilograms of CO2, and the concrete beam is 741 kilograms. And I don't want you to get caught up in the specific numbers here, but the point I'm trying to make is that the functional equivalence with a performance metric of your choice it's really, really important to include that when you're doing comparisons of structural materials. And so here's an example of, we used a performance metric of a single typical floor in a particular live load at a particular elevation of the building and compared a conventional steel framing system to that of a timber framing system. And so we were able to get some numbers to compare. Of course, there's a number of caveats here because this doesn't include foundations and the lower seismic mass and so on and so forth. But for this particular, these handful of performance metrics, this was enough for us to compare the embodied carbon that the architect and the contractor and frankly the owner were very interested in. You can go one step further, right? So you have the system to system comparison, but then you can start optimizing the system itself. So in this example, if you have a steel base system and then you found a way to optimize the steel system, whether that be removing beams where possible or reducing the impact of the concrete topping slab, you can get a reduction from that steel base. And then even in the timber condition, maybe you have a concrete topping slab on the timber CLT panels that you can find a way to reduce the cement content there and further reduce that. But again, I can't stress enough that it's very important for the structural engineer or the architect or the sustainability consultant to make it very clear that you're comparing specific performance metrics. So why do we care about all this? I really don't have to explain to this crowd why this is so important, but it's just worth a reminder that we do, according to the science behind the Paris Climate Agreement and the scientists at the UN who have run a number of different scenarios, we have to get to zero by 2050, and even this plot is a little bit out of date. We now hear that it really needs to be by 2045, or some number in the relative near future, where we have to get to zero. We have to turn the carbon faucet off, or else we'll have irreversible changes to the climate and the planet. And the Architecture 2030 has a nice diagram saying, well, in reality, that's true, but we really have to be at 50% by 2030. And so this all brings us back to the structural material impacts. So when you look at the material impacts, or excuse me, the carbon impacts on a global scale, it turns out that 1/4 of the global CO2 emissions are associated directly with the production of structural materials. So that is yet another one, if you're trying to convince somebody why this matters in the structural world. Just sit with that number for a second. 1/4 of the world's CO2 emissions are associated with the production of structural materials. Again, it's a jarring number that should stick in the back of your mind. One benefit, but an unintended consequence of higher performing buildings where the operational carbon is coming down has really shown a spotlight on the importance and the sort of the percentage of impact associated with the body carbon. And this will only continue in the future unless we do something about it as more and more high performance buildings come online. This is a great plot that I think many of you have probably seen from Architecture 2030. And I think they did a really good job of talking about the so-called time value of carbon, the idea that on day one of the building, nearly all of the impacts associated, or the carbon impacts associated with that building, come directly from embodied carbon, because over time, the operational carbon builds, and it's really summing up the areas below these two curves would give you the overall carbon impact. As I said, I like this plot, but I like to take it one step further, and I've taken some liberties of scale here to say that even over time, though, whether you have renovations or you've had additions to the building, or you replace all the windows, or you replace the MEP systems, excuse me, there will be some sort of step function where the embodied carbon grows over time. And then even on the operational side, it is likely that, say, 20 years in or 30 years in, the owner does replace those windows and makes them higher performing, or the HEV systems are greatly improved. So the gap between the percentage of embodied carbon and operational carbon, I think, is narrowing. And so it's just emphasizing to you all, and I'm probably preaching to the crowd, that the lower you can get the embodied carbon at the beginning of the project will greatly improve the chances that we can get to some of these targets to achieve net zero. Another aspect that's sort of putting the spotlight on the structural engineering is that depending on which study you see or read, for new buildings, about 50% of the embodied carbon is associated with the structure. In this case, this is one study done a few years ago, and about 50% are associated with the substructure and superstructures for all different types: office, school, and hospital. And so getting back to the structural engineer, it's really, we'll be fair. I mean, it's the design team, it's the architects, it's the sustainability consultants, the MEP engineers, but we really influence the project brief because we're sort of connected to everything from initial concepts through construction and even into use and tenant work. So we're really sort of all there, and it behooves us as a structural engineering profession to really up our game because we're talking to everybody. And it's really, most successes come with buy-in from multiple groups. So why would we want to be the one group who's not contributing and buying in? And again, because embodied carbon is happening up front, it's critically important that structural engineers are out in front as well. So here's a very much not to scale plot breaking down buildings, stages, excuse me. So you've got a design phase and you've got a construction phase. And so if you looked at sort of embodied carbon and trying to optimize a system, you could say that early in the design phase, you're going to be reviewing just different systems. And so somehow you'll be making a choice based on review of carbon budgets or some sort of target. And you're going to pick that system. And of course, cost comes into play. And then throughout the design phase, you'll be working on optimizing the system a little bit more and more specifically probably focused on materials. And that's when the specifications with the material requirements for procurement are made. And then finally in procurement, the contractor will do what they can to work with the required specifications. But the reality is at procurement, we're a little bit removed. And so the impacts may improve. They may stay the same, they may worsen. So all the more reason for us to make sure that that initial embodied carbon is as low as humanly possible. The question is, you know, where are we supposed to be? What is the benchmark for that particular system? And more importantly, where's the target? Where should we be aiming? So I'm really excited because I think you're gonna learn a lot from Lauren, who's gonna get into all of this in greater detail. On the structural side, going back to optimizing and system and the role of the structural engineer, is here's a simple chevron frame. We push on it with 100,000 pounds, and we have two braces. One is a Y flange, one is an HSS section. You do a little bit of a comparison on strength, and the wide flange weighs a little bit more, so the HSS member is less. However, the material impacts of HSS, which is primarily from virgin steel versus recycled steel of the wide flange, the global warming potential is much higher for that brace. And so that requires the design team and the owners, and it requires another conversation to figure out, well, what is the best approach here? It probably will be cheaper to go with the HSS, but it's going to have a greater global warming potential. Similar example, somewhat related, is column design in jumbo sections for W14s. Again, this is just one example of many, but you know, in the United States, I'm not sure about Canada, it's probably the same. Grade 65 and 70 for jumbo sections is pretty much not a premium anymore. And they claim that the GWP per ton is about the same, if not less. I don't know, I haven't seen a lot of information on that. The point is, in this particular example, the tonnage is less, going from a 14 by 132 to 109, but the shortening is increased because, as all of you know, they're structural engineers at least, the stiffness of the member, stiffness of steel is not proportional to the strength of the material. It's always the same. So again, as long as you could make that work within the system design and the system performance requirements, you could have a lower tonnage. Here's a classic example of eliminating a transfer. So in this example, you know, the owner wanted a nice retail open space at the bottom, but it comes at a cost, right? So there's 12 additional tons of steel in this particular case. Could the owner have lived with a column in the middle of that retail space? Again, requires early collaboration and conversations with the design team. This is an example of we transferred a 40-story tower on a 10-foot deep plate girder, and simply to eliminate some retail columns or some columns in the retail space below. And again, it was really exciting and really darn cool to design this from a structural standpoint. But in retrospect, I do wonder if I could have done something to maybe convince the owner to eliminate this transfer. We can, as structural engineers, we can get creative. The so-called short transfer, which happens very frequently, where we have a slight offset of a column, we have some sort of residential grid of columns above, and then a different grid of retail or parking below, and there's often these shorter transfers, but perhaps there are options to crank or slope the column and eliminate that additional tonnage. There is some rhyme or reason to this picture. This was an example of really working with the entire team to make this scheme work. So the owner had purchased some land where there was an air rights, so the caissons were built in the 90s, installed in the 90s, excuse me, for a 30-story building, but the owner wanted to put a 40-story building on there. So in an effort to reduce the need for new foundations or foundation modifications, and thus embodied carbon, a lot of embodied carbon, we worked with the planners in the program to sort of crank a few columns and push some loads, have some load shedding onto some of the caissons that had reserve capacity. So it's an example of early on collaboration. Here is another option that structural engineers can look at, and that's merging the so-called virtual work with the minimum strain energy. Minor changes to the bracing is a material reduction of 5%. Of course, there are caveats here because there's all sorts of connections and gusset plates to deal with, but I think, you know, the idea though is that coming with options to reduce the material impacts. And then finally, this is the classic example here in the US, the concept of performance-based concrete mix designs is really starting to pick up steam, allowing us to reduce the cement content and thus reduce GWP. What we are contending with is a profession that's not used to new issues of workability and potential finish and primarily construction sequence, as these lower heat of hydration mixes have a longer strengthening associated with them. So I do want to thank you. That was sort of an introduction to the impact of materials and the important role that the structural engineer plays. And I'm very, very excited to hand off to Lauren, who's going to talk all things SE 2050.